Hi, Assalamualaikum and very good day. My name is SYAZWINA BINTI SA-HARIFF. Will be present to you our lab report, which is E4 Common Collector Amplifier Emitter Follower. The main objective of these experiments are to measure the input and output impedance of the common collector amplifier, to study the phase relationship between the input and output signal of the common collector amplifier, and to measure the power gain of the common collector amplifier. The equipments used in these experiments are dual-channel oscilloscope, function generator, 12 volt of DC power supply, digital multimeter, potentiometer 500 ohm, project boards with connecting wires, resistor 3.3, 12 and 470 kilo ohm, transistor, capacitor 22 microfarad 50 volt and 100 microfarad 50 volt. The procedures required in these experiments are: in part 1 of the experiment, we were calculating and measuring the DC operating voltage found in a common collector circuit. First, the circuit as shown in figure 1 is connected. Potentiometer R4 is not connected at first. The DC collector supplies voltage VCC is adjusted to 24 VDC. The AC input voltage should be 0. The DC voltage between the base of Q1 and ground is measured. The DC voltage between the emitter of Q1 and ground is measured. Then, the emitter current is calculated. The DC voltage between the collector of Q1 and ground is measured. The collector to emitter voltage VCE of Q1 is then calculated. In the part 2 of the experiments, where we will measure voltage gain and input impedance of the CC amplifier. First, the signal generator is set to the sine wave function at a frequency of 1 kHz. The amplitude of the function generator is slowly increased until the output voltage Vout is about 150 mV peak to peak. The settings remain the same until completing the experiment. The input voltage Vin is measured, then the value is recorded in table 1. The voltage gain, the input impedance, input current, the input power is calculated. Then the DC load line analysis graph for common emitter configuration is drawn, and the Q point of transistor operating is determined. On the same graph, Vin and Vout wave signal and their amplitudes is sketched based on the experiment setting. For the part 3 of the experiments, we measure the output impedance of the CC amplifier. First, R4 is inserted back to the circuits, and potentiometer is adjusted until Vout is half of the value obtained in part 2. VCC is returned to the 0, and R4 is removed from the circuit without disturbing the setting of R4, and its resistance is measured using the digital multimeter. The value of the R4 is equal to the output impedance Rout of the amplifier. Then, the output power Pout is then calculated. For the part 4 of the experiments, we calculated power gain of the CC amplifier. First, the power gain is calculated and recorded according to the equation below. Lastly, in the part 5 of the experiments, we determine the phase relationship between the input and output signal of the CC amplifier. Both channel on the oscilloscope is used to display the input and the output signals of the CC amplifier. The real picture of the waveform obtained is captured. The phase difference for the two signals is determined.
Assalamualaikum and hi everyone. My name is NURHANISSA binti Abdul Halim. I will talk about the data and analysis common collector amplifier emitter follower. For the next slide, I will show you guys our group data and analysis for this experiment. For the part 1, calculating and measuring the DC operating voltage found in a common collector circuit. First, we have to calculate the emitter current IE. The formula are given: IE equal to VE over R3. VE we get from the DC voltage between the emitter, while the RE we get from the figure 1. So the answer is 1.15 milliampere. Next, we have to calculate the collector for emitter voltage VCE of Q1. VC we get from the DC voltage between the collector of Q1, while VE we get from the DC voltage between the emitter. So the answer of our group is 12.74 volt. For the part 2, voltage gain and input impedance of the CC amplifier. First, we have to calculate the voltage gain AV. The formula are given: AV equal V out over V in. So the answer is 3.49 millivolt. Next, we have to calculate the input impedance R in. To calculate R in, we must know R1, R2 and R3. So we must insert R1, R2 and R3 from the figure 1 into the formula R in equal to 1 over R1 plus 1 over R2 and 1 over R3. So the answer we get is 191 ohm. For the input current I in, for your information, IB equal to I in, so that we can conclude I in equal to V in over R in, and the answer is 0.22 milliampere. Last, for the part 2, we must calculate the input power P in. P in equal to V squared in over P in, and the answer is 0.17 milliwatt. For the next slide, that is our DC load line analysis graph. For the part 3, for output impedance of the CC amplifier, we have to calculate output power. So the answer is 15.63 millivolt. And for the part 4, power gain of the CC amplifier, the formula is AP equal P out over P in. So we get our answer is 6.95, and we can conclude that our actual answer and our final answer is 7. For the part 5, the phase relationship between the input and output signal of the CC amplifier. From the picture, we can conclude there is no phase difference between two signals.
Hi, my name is Bryan, and I will be briefing on the quiz, discussion and conclusion part. So for the quiz, the first question is: the common collector circuit is used mainly as an impedance matching circuit. For the second question, the input AC signal is applied between the emitter and the base. For the third question, the AC voltage gain is high. For the fourth question, the output impedance is low. For the fifth question, the CC circuit is also called an emitter follower. It's because that the output voltage has no phase difference compared to the input voltage. Next, going into the discussion, we would like to give an explanation using a theory on the Q point that we got on the graph. So from the graph, we get that IBQ is equals to 1.2 milliamperes and VCEQ is equals to 12 volts. So by using theory or Thevenin's theorem, we can reduce the DC analysis on the left into the circuit on the right, with Thevenin voltage is equals to 12 and Thevenin's resistance is equals to 195 ohm. So on the right hand side, we can see there is two loops. and for each respective loop we can use Kirchhoff voltage rule to get an equation, and by substituting the values that we got from experiment and assuming that the voltage between base and emitter is 0.7 volt, we get that IBQ is equals to negative 3.6 milliamperes plus or minus 5.1 milliamperes. This doesn't mean that the current is in the opposite direction, because the positive current is still within the range of error of IBQ. Similarly, for loop 2, we can apply Kirchhoff voltage rule, and substituting the value we get VCEQ equals to 12 volt plus or minus 1 volt. Both of the values in the table agree within this range of error of the theoretical calculation. This means that the Q point value that we obtain can be explained using Kirchhoff voltage rule, and by assuming that the voltage across base and emitter is 0.7 volts, which means that the transistor is made out of a diode and it's made out of silicon. Next, we want to discuss on the application of CC amplifiers. From the experiment, we get that the values for both input and output impedance is the resistance for input is 191 ohm, while the resistance for output is 3.6 ohms. This shows that the common collector amplifier can be used as a circuit when it needs to connect a high impedance input to a low impedance output. This will make the circuit to have a high current gain, which is why common collector amplifier is also called as a unity gain buffer amplifier. Now, going on to the conclusion, the emitter voltage is equal to 12.74 volts plus or minus 0.02 volts. From the graph, the Q point value is IBQ equals to 1.2 milliampere, while VCEQ equals to 12 volts, respectively. The output power of the circuit is 15.63 milliwatts, and the power gain from the circuit is roughly 7. Lastly, there is no phase difference between the input and the output signals as agreement from the theory.